Hello everyone, today we'll be covering UV spectral regions and its importance along with two numerical problems. For the contents we'll be covering today, we'll be covering electromagnetic spectrum and in specific UV and its spectral region. We'll be covering the spectroscopy method. We'll be covering how electronic transitions work. We'll be covering Beer's law and we'll be doing two numericals. The electromagnetic spectrum is a spectrum of electromagnetic radiation ranging from cosmic rays to radio waves or background radiation. Basically, cosmic rays have a order of magnitude for wavelength from 10 power minus 12 meters, and radio waves have the order of magnitude of wavelength at 1 meter. The UV spectral region lies between 100 nanometers and 400 nanometers wavelength. Within the UV spectral region, we have three different ranges. The UV range A ranges from 315 nanometers to 400 nanometers. UVB ranges from 280 nanometers to 315 nanometers. UVC ranges from 100 nanometers to 180 nanometers. All of these are wavelengths of the electromagnetic radiation within the UV spectrum. Further, to have a simplistic classification, we can classify electromagnetic radiation within the UV spectral region into long UV and short UV with 350 nanometers to 400 nanometers, 100 nanometers and 315 nanometers respectively. So basically, spectroscopy is the study of interaction of electromagnetic radiation with our analyte sample. So basically, investigation and measurement of spectra by comparison before and after interaction with matter is known as spectroscopy. Specifically, we use electromagnetic radiation within the UV spectral region for type of spectroscopy known as absorption spectroscopy. In this type of spectroscopy, we measure the intensity of light before and after absorption, and this is varied as a function of frequency or wavelength. So then we examine the minima and maxima of our spectrum. Further, our atoms and molecules can absorb energy. For UV spectral region, electronic transitions occur. The electronic transitions that occur can be classified by the type of transition in the different types of covalent bonds, and each of these transitions have a different amount of relative energy requirements. So a sigma to sigma star anti-bonding transition requires very high energy with around the approximate region of UV spectrum required being around 150 nanometers, whereas a non-bonding electron to a non-bonding electron level to a sigma star anti-bonding level would require around 150 to 250 nanometers and high, which is a relatively high energy, whereas the lowest energy required would be from a non-bonding orbital to a pi star anti-bonding orbital. And these electronic transitions help us to identify the type of molecules in which the different types of bonds are present. Single bond molecules have only sigma bonds, which would characterize sigma to sigma star transitions. Similarly, the other types of transitions and their energy requirements are present on the screen. Apart from the identification of molecules as a function of their minima and maxima values of absorbance plotted against their wavelengths or frequencies, UV spectral region radiation can also be used for disinfection and sanitation of various laboratory surfaces and apparatus. To perform absorption spectroscopy, we need to have a governing principle for the absorbance, which is known as Beer's law. So before we proceed to the principle of Beer's law, certain assumptions are made. The first assumption is that the absorbing molecules don't interact with each other, they are assumed to be inert, and any reaction or no reaction is said to be happening. So the second principle is that it is applicable only for dilute solutions, and the third principle is that only monochromatic wavelength must be used. That is, only a single wavelength of UV spectrum must be used. This can be achieved by using a monochromator in the instrumentation part. So Beer's law states that the absorbance of a sample is directly proportional to the path length and the concentration of the sample. So absorbance can be equated using a sample epsilon and multiplied to the path length and concentration of its concentration of the analyte sample. Further, absorbance can be equated to the negative log to the base 10 of the transmittance of the sample. The transmittance is said to be equal to the incident intensity of radiation divided by the outgoing intensity of the radiation, and this is known as transmittance. So let's proceed to numericals. For our first question, we have a solution that has molar absorptivity is equal to 120 liters per mole centimeter, concentration is equal to 0.2 moles per liter, and path length is equal to 1 centimeter, which is basically the standard length of a quartz cuvette. So from this we need to calculate the absorbance. For this we need to use Beer's law. So in Beer's law we have the formula A is equal to a molar absorptivity multiplied by path length multiplied by concentration. So here we have multiplied 120 by 0.2 multiplied by 1, which gives our absorbance is equal to 24. For our final numerical, we have a sample that transmits 25% of incident light. So here we need to calculate the transmittance and the absorbance. To get the transmittance, it is pretty straightforward, as transmittance is basically the amount of light that passes through our sample after absorption. Here we can directly get the transmittance value by dividing 25 by 100 to get 0.25. So 0.25% of our light is passing through our sample. Finally, to get absorbance, we can use Beer's law, where if we substitute the value of transmittance into the negative log base 10 of the transmittance, we get a absorbance value of 0.602. So finally, I'd like to thank you for watching this video and hope you understood the principles of UV spectrum and its importances along with the numericals of Beer's law.